While a vertical asymptote obviously runs vertically and was the line x equals a number, your horizontal asymptotes are going to run horizontally and therefore should be y equals some number. They use the letter b to represent that it could be any number. Okay, says that these are going to occur if your f of x, remember f of x is like your y, right? If your y value approaches b, as x is either going to positive infinity or if it's going to negative infinity. So here it's your x value is going to positive, negative infinity, while your y value will be approaching some particular number. All right? So they put together some tables for us for this particular function. So it says, as y approaches blank. Remember, f of x is the same thing as y. So I'm looking at the second column here. All right, looks like we started at -1. Then I went to negative 0.125, negative 0.0102, negative 0.001. What am I getting closer and closer to? 0. Okay, so I would say that we are approaching 0 in our y column. Then they ask, what is our x approaching? So it went from -1 to negative 1,000. So where is it headed?
Negative 10,000?
Where? Negative infinity. Okay. All right. Same thing for the next table. They ask about y. Again, y is our f of x column. It started at 0.3 repeating, and now it's at 0.0009. So it's getting closer and closer to 0. And we started at +1, and now we're at positive 1,000. So where is this one headed? Positive infinity. Good. Okay. Therefore, since both y values are approaching the same number, but our x is going to negative and positive infinity, we can say that we will have a horizontal asymptote at that y value. Again, remember, horizontal lines, when you graph them, are y equals a number. So that's why we're looking at the y value here. Okay. So now it says, looking at the end behavior of f of x. It says, what happens to f of x? Again, remember, f of x is your y. So they're saying, what happens to y, or your overall function, as x gets sufficiently large or small? Okay, well, what's going to happen is we can see this by rewriting f of x. So rewrite your equation by dividing both numerator and denominator by the highest power of x. So whatever your biggest exponent is, okay? So let's see here. We're going to do that for example 1 and see what happens, and we'll do it for example 2 as well. So it says we're going to rewrite the whole function dividing both this top part and this bottom part by the biggest exponent we see. Well, what's the biggest exponent in this equation? The x squared, okay? So I'm supposed to divide both the top and the bottom by that. So I would rewrite this as the top divided by x squared over everything in the bottom divided by x squared. All right. So if we were to say that the value of x is getting either really, really big or really, really small, they want us to determine what we think would happen. Okay, well, if x is not that big, let's say x is just 1. In the top, that would become 4 over 1, which is just 4, right? Okay, but what if x was getting bigger, like x was 10? If I plug in 10 for x, 10 squared is 100, right? 4 over 100, that's a pretty small number, right? Or even if it was negative 10, still the same outcome because negative 10 squared is still 100, right? If it gets even bigger, if we said that x squared was 1,000 squared, that's an even smaller decimal or fraction, right? So the top is going to keep getting smaller and smaller and smaller, kind of like this was, right? So the smaller it got, the closer it got to what number? 0, right? So if that bottom number, or if the part we plug in for x gets really, really big or really, really small, it's just going to turn the top into getting closer and closer and closer to the number 0, right? Okay. Over. Well, right here, it does not matter what number I plug in for x, I'm going to get that number over itself, right? And any number over itself always simplifies to 1. Okay, so I'll have 1 plus. Then this next one, well, the same thing is going to happen here that happened here, right? Whatever number I plug in here, the bigger or smaller the number gets, it's going to make this get closer and closer and closer to what? 0. Okay? So if we were to simplify this, I would have 0 over 1, and 0 divided by 1 simplifies to just 0. Okay? So this was as x increased or decreased, right? Didn't really matter because it was squared. This is what occurred, right? So as x increased or decreased, we're going to say that the function 4 over x squared was headed towards 0. Okay? All right, now we're going to do the same thing for number 2. Okay, but on number 2, what's the largest exponent of a variable here? Just 1, right? The linear term x, right? These have understood exponents of 1, right? So I'm only going to be dividing by the term x. So just like in the last problem, we're going to do it to everything. So everything in the numerator is going to be divided by x. And same for everything in the denominator, divided by x. Okay. All right, so for this first one, kind of similar to what we said would happen here, right? Whatever the x is here, the one in the bottom will be the same. So it doesn't matter how big or small it gets. Anything divided by itself becomes 1, right? But then it's also going to be multiplied by 2. Well, 2 times 1 is just 2. Okay, so that first part will become 2. What about in that second fraction? If I make x really, really big or really, really small, where am I headed? 0. It'll take a little bit longer than it did when it was squared, but I'm going to get closer and closer and closer to 0, right? Okay? All right, in the bottom, x over x is going to get to be what? 1, right? Because anything divided by itself is 1. But that 1 over x, again, is going to go to 0. All right. So this would be 2 plus 0, which would just be 2, over 1 plus 0, which is 1, which simplifies to just 2. Okay? So we actually have a rule that we might can come up with here. Let's look at one more example and see if we can determine what we think our rules should be. All right, we're going to try this process one more time. On number 3, what's the biggest exponent you guys see? The x squared. So I'm going to divide everything by x squared. All right. X squared over x squared is going to be what? 1, right? Whatever it becomes, it's itself over itself. Good. Okay. What about 9 over x squared? What's that going to get closer and closer to? 0. Over, what about x over x squared? Where's that going to become? So I might plug in 5 for x. That'd be 5 over what? 25. Or if I plug in 10, that'd be 10 over 100. Or if I plug in 20, that'd be 20 over 400, right? So what value am I getting closer and closer to? 0, right? 5 over 25 is a little bit bigger than 10 over 100, a little bit bigger than 20 out of 400, right? So it keeps getting smaller and smaller and smaller and smaller. So it becomes 0. All right, and what about 2 over x squared? Where's that headed? 0 as well. All right, so I got 1 minus 0, which would just be 1, over 0. Well, are we allowed to have 0 in the bottom of a fraction? No, so this is undefined, right? Okay, so we actually do have a rule here. Okay, it says, so summing up the asymptotes of a rational function so that we don't have to plug this in and check it every single time, says let f be the rational function expressed by this term, just whatever your p of x over q of x is, okay? If you notice in the numerator, they use the letter n to represent the exponent. In the denominator, they use the letter m to represent the exponent. Okay, it says where p of x and q of x do not have any common factors, so not any way I could simplify it, okay? It says the graph of f will have vertical asymptotes. We learned this on 6.1 at the zeros of q of x. Remember we said that the vertical asymptotes came from the denominator, which is where q of x is. Okay, but we want a rule for our horizontals because we don't want to have to plug this in and check every single function every single time. So here it says if n is less than m. Well, again, n is in the top, m is in the bottom. So they're saying when the top is less than the bottom. Okay? So if you look here, this one, the top was bigger than the bottom, right? Okay? Then look at number 2. The top and the bottom were the same exponent. But here, it was bigger in the bottom than it was in the top, right? Okay, so the top was less than the bottom. In this scenario, what did we end up saying our horizontal asymptote would be? 0. Okay, so if the exponent on top is smaller, then you are going to have a horizontal asymptote on the x-axis, which is the line y equals 0. So when the larger is in the bottom. Okay, we do have a little acronym to help us remember this. Okay, so this acronym stands for bigger on bottom. Then we get O, or 0. All right? So, bigger on bottom, we get 0 as the horizontal asymptote. Okay? Next, it says if n equals m. So that means the exponents in the top and bottom are the same. Well, that happened to us on example number 2, right? On example number 2, the exponents were the same. We ended up getting 2. Well, if you guys notice, the two things that had the x's were 2 as a coefficient and 1 as a coefficient, right? 2 divided by 1 is what gave us the 2. So if the exponents are the same, then your line, your horizontal asymptotes line is just going to be whatever the top coefficient is divided by the bottom coefficient. I used A and B because that's what they used here. They used the letter A and B as coefficients in this equation. Okay? We do have one for this one too if you want an acronym. This one is EATS DC. So this stands for exponents are the same. So exponents are the same. Then we will divide the coefficients. All right, then the last possibility is that the exponent in the top, the letter N, was bigger than M. And that's what happened to us on example number 3, right? If you look up here at example number 3, the exponent in the top was 2, the bottom was only 1. And what was our outcome here? Undefined. So in this scenario, if the top exponent is bigger, then there will be no horizontal asymptote. Acronym for this is BOTN. This one stands for bigger on top, then we have none. All right. So bigger on bottom, what happens? What do we get? 0. Bigger on top, undefined, right? We don't have one. Good. All right, and then if they're the same, what am I going to do? Divide the coefficients. Okay, so let's take a look at these examples down here. So horizontal asymptote, that's the 3 rules that we just learned today. On number 7, are the exponents the same or different? Same. So exponents are the same. This is EATS DC. What did it say we would do with the coefficients? Divide them. Okay, so the coefficient here is 2. The understood coefficient down here is 1, right? So 2 divided by 1 tells us we're going to have a horizontal asymptote at 2. All right. Now, vertical asymptote. Remember from 6.1, your vertical asymptote comes from the denominator, right? So this is x plus 1. Just like our factors, we set it equal to 0 and solve. So where am I going to have a vertical asymptote? Right. Remember, this is x equals a number because it's a vertical line. Okay? All right, for number 8, bigger on top, bigger on bottom. Bigger on bottom, so what does that mean? 0. Okay? And then if we try and solve the bottom down here, take that bottom, set it equal to 0. I'd subtract 1, right? Okay, so I'd have x squared equals negative 1. Then what would I have to do? Take a square root, right? Can I take the square root of a negative number? So that means we won't have any vertical asymptotes. Okay, number 9, bigger on top, bigger on bottom. On top, so what does that mean? Right, so we won't have any. All right, and then on the bottom, that's what gives me my vertical. I set it equal to 0. Where are we going to have a vertical asymptote? At 2. Nice. All right, so bigger on top means what? Bigger on top? Right, none. Bigger on bottom? 0. If the exponents are the same, we're going to divide the coefficients.